Welcome everyone. Let's begin our lesson for today by going over our learning goals and success criteria. First, what are we learning? We're learning how to determine how base values, coefficients, and constants will affect the graph of an exponential function, how to graph exponential functions, how to graph linear inequalities using slope and y-intercept, and how to use the correct line and shading for graphs of inequalities. How are we learning it? Through the Exponential Functions Review Notes and Exponential Functions Review Assignment, the Graphing Linear Inequalities Part 3 Notes, and the Graphing Linear Inequalities Part 3 Assignment. When can we use this information? To calculate the amount of money in a savings account, including interest, and to determine which scores you can receive on your final exam that will allow you to pass the course. How do you know you learned it? By getting a score of 4 on the Exponential Functions Review Assignment and a 4 on the Graphing Linear Inequalities Part 3 Assignment. We will begin by going over our learning goals and success criteria. While we do that, you'll fill out your Get It Started. Once you're done with your Get It Started, we'll go over it together and answer any questions that you may have. Then we'll go over the Exponential Functions Review Notes, and then after that you'll complete the Exponential Functions Review Assignment. Once you've completed the assignment, we'll go over it together and answer any questions that you may have. With about 10 minutes left of class, we'll go over the Graphing Linear Inequalities Part 3 assignment. And then at the end of class, we'll go back over our learning goals and success criteria, and while you fill out your before you go, your homework is to complete the Graphing Linear Inequalities Part 3 assignment and any incomplete assignments that you may have. Let's take a look now at our Exponential Functions Review Notes. Our notes begin with the learning goals and success criteria. Now, what is an exponent? An exponent is a number that tells you how many times to multiply the base number by itself. So for instance, we have 2 to the third power. 2 is what we call our base number, and it tells us that we're going to multiply 2 times itself 3 times. So that's really 2 times 2 times 2, which is 8. Now let's talk about positive exponents. So positive exponents mean that the number above here, the number of times we're going to multiply it times itself, is a positive number. So we have 5 squared. Well, that means that we're multiplying 5 times 5. Which in this case is 25. Then we have 5 to the third power, which is 5 times 5 times 5, which is 125. And then 5 to the fourth power is 5 times 5 times 5 times 5, which is 625. So we can do this with any exponent. We can take any base number and raise it to an exponent and multiply it by itself a certain number of times and solve. Now what about 0 and 1 exponents? So 5 to the first power. Well, 5 to the first power is just 1 5, right, times itself, so 5, that's it. So that's just 5. Now 5 to the 0 power. So there's 0 5s, and that's equal to 1. Now please make sure that you understand this. Any number raised to the 0 power will always be 1. So not 0, but 1. So 5 to the 0 power is 1. 2,000 to the 0 power is 1. 200 million to the 0 power is 1. So any number raised to the 0 power is just 1. Now combining like terms, if we look at this, we're going to combine like terms, and the rule is in order to combine like terms, they have to have the same exponents and same variables. And if they do, we're going to add the coefficients. So for instance, we have 2x and x. Well, they're both x's, so they have the same variables, and they have the same power, same exponent. Really, it's imaginary exponent of 1. So we can just add these. 2x plus x is 3x. We have 3x squared plus 4x squared. Again, same variable, they're both x's. And the powers match, so we just add the coefficients. That's 3 plus 4, which is 7x squared. We can do it with subtraction as well. So we have 6x cubed minus x cubed. Well, again, same variable, same power. So now we can go ahead and subtract. So 6 minus 1 is 5x cubed. Now we have 7x to the fourth minus x cubed. Well, again, same variable, but this time they do not have the same power, so we cannot combine them. It just stays 7x to the fourth minus x cubed. Now, when we multiply or divide exponents, so the rule is this: when we multiply or divide exponential terms even if they do not have the same exponents but have the same variable. We can still do it. The rule is we multiply or divide the coefficients and add or subtract the exponents. So if we're multiplying, we're going to add the exponents. So this is 2 times 1, so that's my coefficient. And I have an x to the first and an x to the first, so I'm going to add those exponents. So I get 1 plus 1 for my exponents. So 2 times 1 is 2, and 1 plus 1 is 2, so it should be 2x squared. Let's look at another example of multiplication. So we have 3x cubed times 4x squared. Now with this one, again, we're going to multiply the coefficients, so 3 times 4, and we're going to add the exponents, so 3 plus 2. We end up with 3 times 4, which is 12x, and 3 plus 2 is 5, so we get 12x to the 5th power. Now division is just the opposite, so we're going to divide the coefficients and subtract the exponents. So we get 6x to the 7th divided by 2x to the 3rd, so we're going to divide the coefficients, so 6 divided by 2, and then subtract the exponents, so it's x to the 7 minus 3rd power. So 6 divided by 2 is 3, and 7 minus 3 is 4, so we get 3x to the 4th. Now here we have 7x to the 4th divided by x cubed. So again, we're going to divide 7 divided by 1, and x to the 4th minus 3, which is 7 divided by 1 is 7, and x to the 4 minus 3 is first power. And whenever it's the first power, we don't need to put it there, so it's just 7x. Now what if we have the coefficient and variable inside of parentheses and the power outside? Well, when we do that, we're going to raise the power by multiplying the exponents. So in this case, we have 2x, and this is x to the first, and we're going to multiply the powers for each of these. So this is really 2 to the first power times 2, and x to the first power times 2. So that's really 2 squared times x squared. Well, 2 squared is 4, and x squared is just x squared, so it's 4x squared. Let's look at this one. Again, same thing. This is 3 to the first and x to squared. So we're going to multiply each of those by the power out here, which is 3. So we got 3 to the first times 3 and x to the second times 3. Well, we know that 3 to the first times 3 is 3 cubed, and 2 times 3 is 6. So we got 3 cubed times x to the 6th, and 3 cubed is 27. So it's 27x to the 6th. Now for this one, we have x squared times y cubed, and we want the whole thing squared. So again, we're going to multiply it. So x squared times 2, and y to the 3rd times 2. And we get x to the 4th, y to the 6th, because we multiply 2 times 2 is 4, and 3 times 2 is 6. Now we have x, y squared, z cubed to the 6th. So we're just going to multiply each of the exponents by 6. So we get x to the first times 6, and y to the second times 6, and z to the 3rd times 6. And we're just going to multiply these out. So 1 times 6 is 6, 2 times 6 is 12, and 3 times 6 is 18. So we should get x to the 6th, y to the 12th, z to the 18th. Now let's take a look at negative exponents. So a negative exponent looks like this, where it's 5 to the negative 2nd power. Now here's the rule with negative exponents. When we're working with a negative exponent, we're going to rewrite as the reciprocal, meaning instead of this being 5 to the negative 2nd, we're going to write it as 1 over 5. And then we're going to change the power to a positive. So 5 to the negative 2nd becomes 1 over 5 squared. So I made the power positive and put it under 1. Now I just do it like normal. So 5 squared is 25, so this is 1 over 25. Now 3 to the negative 3rd power. So again, that becomes 1 over 3 to the positive 3rd power. 3 to the positive 3rd power is 27, so it's 1 over 27. Now we have x to the negative 6th power. So we're going to flip that and it becomes 1 over x to the positive 6th power. Now let's take a look at fractional exponents. For instance, we have 25 to the 1/2 power. So what we're going to do is we're going to take the base number, 25, and we're going to raise it to the power of the numerator. So it'll be 25 to the first power. And then the denominator is going to make up the root we're going to take. So in this case, it'll be the second root or square root. So the way that looks is we're going to have 25 to the first power, which is just 25. And then we're going to take the square root of that, just like this. So we need to know what number multiplied by itself gets 25. Well, we know that 5 times 5 is 25, so the square root of 25 is 5. Let's look at another example. We have 3 to the 1/3 power. So again, we're going to take 3 to the first, and we're going to find the cube root of it. Well, what times itself 3 times equals 3? Well, we should recognize that it doesn't come out evenly. There's no whole number that does that. So we're just going to leave it as cube root of 3. Now we have x to the 2/3 power. So what we're going to do is we're going to take x and raise it to this power. So it should be x squared. And then we're going to take the cube root of that. So the third root of x squared. And we should notice that there's no number that we can multiply by itself 3 times to get x squared. So we just leave it as cube root of x squared. Now what if we have a negative and a fractional exponent? Well, we do the same thing we did on the previous two. We're going to go ahead and flip it and make it positive. So we're going to, x to the negative 1/2 becomes 1 over x to the 1/2 power. Just like that. Now we know that we're going to take the 1/2 power, and that becomes x to the first, and then we're going to take the square root of that. So that becomes 1 over the square root of x to the first, which is just x. Now, first of all, what is a linear function? A linear function occurs when the graph of a relation set forms a straight line. So when we plot the points, if it forms a straight line like this, that means it is a linear function. Now, what does a linear function look like as a table? Well, if we look at the table here, the rule is if all of these in each column, so this column and this column, if the change is all consistent and it's addition, then we say that the set is linear. So for instance, we have 1, 2, 3, 4. So we can see that it is consistent, there is a consistent pattern, and the pattern is that we're adding by 1. So that's addition. So now if we look at this side, we have 2, 4, 6, 8. Again, consistent pattern, addition by 2. So is there a steady change in the number of months? Yes, we're changing by 1 month each time. Is there a steady change in the amount of rainfall? Yes, there is. We're changing by 2 each time. So therefore, we could say, yes, this set is linear. And if we were to graph it, it would look something like this and form a straight line. So that's a linear function based on a table. Now from graphs, again, the rule is they form a straight line. So this is an example of a linear function. This is also an example of a linear function. As is this one. It can go up or down. It can be really steep or really flat. This is another example. Again, really flat and going downward. This one's steep and going downward. So all of these form what we call linear functions. Now, how can we recognize linear functions as an equation? Well, it should be able to form y equals mx plus b. Or it could be f of x equals mx plus b. An example of this would be y equals 1/2 x minus 3. This would be an example of a linear function. Notice the powers for both y and x are 1. Now what is an exponential function? An exponential function is a function that forms a curved line that has a line that it will never cross. For instance, this is an exponential function. It's a curved line, it's a single curve, it starts low and works its way up. It could go this direction also, start high and work down. But it has a line it never crosses. Notice this line gets really flat here at the x-axis. It will never cross the x-axis. So there's a line here that forms that it'll never cross. In this direction, it'll keep going and going and going and get really steep. How can we recognize exponential functions from a table? Well, first of all, the rule is the number of months, my x values, should be changing by a consistent amount, and it should be addition. And my y values should be changing by multiplication. So in this case, we have the months. So this is 1, 2, 3, 4. Well, is there a steady change in the number of months? Yes, there is, and it's changing by 1 month each time. Now here we have 2, 4, 8, 16. There is a steady change, and it is multiplication. We're multiplying by 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So we're seeing a steady change, and it's multiplication. It is doubling, or multiplying by 2 each month. So therefore, is this exponential? Yes, it is. And if we were to plot these points, it would look something like this and form this curve. Now, what do exponential functions look like as graphs? They always form a curve, a single curve. So for instance, this is an exponential function. This, even if I shift it over, it's still considered an exponential function. If I have it go downward, that's an exponential function. And if I have it go below the x-axis, still an exponential function. All of these are examples of exponential functions. Now, exponential functions are of the form y equals a to the x times b. Or it could be f of x equals a to the x times b. Here, an example of this is y equals 3 to the x times 4. Now, if you notice in all of these, y has a power of 1, and x is the power of the base number. So these are exponential functions. So how can we compare these? So the question says, based on the table below, does each table represent a linear function, exponential function, or neither? Well, if we look at this one, we have 1, 2, 3, 4, 5. So this one's consistent and going up by 1. So it could be either linear or exponential at this point. Then we have 3, 6, 12, 24, 48. Well, 3 plus 3 is 6. 6 plus 3 is not 12, so it's not linear. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So that means it's got to be exponential. Now this one, 2, 4, 6, 8, 10. So we do have a consistent pattern. We are adding by 2. So it could be either linear or exponential. Then we have 1, 2, 3, 4, 5. Well, 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1 is 5. So they're both consistent, they're both addition, therefore it's got to be linear. Now this one says -2, -1, 0, 1, 2. So again, we're adding by 1 each time, so it could be either linear or exponential at this point. Then we go 8, 4, 0, 4, 8. So here we subtracted 4, then we added 4, So it's not a consistent pattern, so therefore it's neither linear nor exponential. Now we have our graphs. We're supposed to determine whether it's linear, exponential, or neither. Well, this first one does have a curve, but it curves in both directions, which we know that exponentials only curve in one direction, so therefore this is neither linear nor exponential. Then this one, we have a straight line. Well, we know a straight line forms a linear function, so that one is linear. This one has a single curve, so that one is exponential. Now, looking at the equations, we have y equals 2/3 x minus 4. Well, both of them have a power of 1, and we have both the x and y, so that one we said was linear. It also looks like y equals mx plus b, so we know it's linear. Now this one is y equals 2/3 times -4 to the x power. Well, we should notice that looks like b times a to the x, which is exponential. So this one is an exponential function. This one says y equals 2/3 times the absolute value of x minus 4. Again, it looks similar to this one. We have x to the first power and y to the first power, but the absolute value changes things, so it is neither linear nor exponential. Now, let's take a look at exponential functions with bases less than 1. So when the base of an exponential function is less than 1, the curve will remain above the x-axis, and the curve will be the same, but the curve will go down instead of up. For example, we have y equals 1/3 to the x power times 4. So notice this is smaller than 1, and a normal curve goes up, but if we have a value here, a base number less than 1, it's going to go downward as we go from left to right. So it looks exactly the same as 3 to the x, except it's just mirrored over to the other side and going this direction. Now what if the base is negative? Well, when the base is negative, the graph will flip below the x-axis and will go down instead of up. For instance, we have y equals negative 3 to the x times 4. So here, it's going to flip and go downward below the x-axis. It's going to be exactly the same graph as 3 to the x, but it's just going to be down this direction. So it's going to be like it was reflected down below the x-axis. Now what if we were to add a constant? So when a constant is added to an exponential function, the graph will shift up or down, but the curve will stay the same. So if we had y equals 3 to the x times 4 plus 2, then it would look like this. So it would look exactly the same as y equals 3 to the x times 4, except we're going to slide it up 2 units. So now the line it doesn't cross is y equals 2 instead of the x-axis. Now, what if it was 3 to the x times 4 minus 2? Same thing, except now it's going to shift down and go this direction. So it's the same as 3 to the x times 4, except we're going to slide it down, and now the line it won't cross is y equals negative 2. Now, what if we do a sum of exponents, meaning we add something to the exponent? Well, that will cause the graph to shift to the right or to the left. So for instance, we have y equals 3 to the x plus 2 times 4. So what that should look like is, notice it's the same curve, and because this is in the exponent, we're always going to go opposite. So you would think that we'd go x plus 2 means we're going to slide to the right. But because it's in the exponent, we're going to go opposite. So it becomes x minus x plus 2 becomes a shift to the left. So notice it's the same graph as 3 to the x times 4, except we slid it to the left 2 units. Now what if it was 3 to the x minus 2 times 4? Well, same thing. We're going to slide it, but this time we're going to slide it to the right 2, because we always go opposite when we talk about exponents. So we slide it to the right 2, and it becomes this graph. It should look exactly the same as 3 to the x times 4, except we're going to slide it to the right. There's a video here that shows you how to check exponential functions in Desmos, so you can go ahead and watch that video as well. Now, what is exponential growth? Exponential growth is a function where a quantity increases by the same rate in each time period. For an example, money in a savings account. So I put money into my savings account, my money increases with interest, and it goes up exponentially. Now, what is exponential growth formula? The exponential growth formula is f of x, or y, is equal to a times 1 plus r to the x power. So a is our starting amount. That's how much we start with. If we were talking about money in a bank account, that's how much money we put into the account. R is the rate of change, meaning how much interest are we gaining. X is the amount of time. So let's say it goes monthly and we're doing it over 12 months. 12 months would be my x. Now notice the value inside the parentheses will always be greater than 1 with exponential growth because I'm adding 1 plus some number. It doesn't matter what number that is, it won't be negative. So we know it'll always be greater than 1. So let's look at exponential decay now. Now exponential decay is a function where a quantity decreases by the same rate in each time period. An example of this would be radioactive decay of a fossil. So when something dies, it eventually becomes just bones, right? We know this through archaeology. It becomes just bones. And what happens is there's a certain amount of carbon in that bone. After a while, the carbon starts to decay. It starts to wither away. It starts to evaporate. From there, we can tell how old the fossil is based on the amount of carbon that's still left. So that's radioactive decay of a fossil. Now, exponential decay, the formula looks like this. F of x equals a times 1 minus r to the x. So it's the same as growth, except this is minus r instead of plus r. A is still the starting amount. That's how much we start with. So If we were talking money that we owed, well, that might be A, right? So that's our starting amount, how much we owe. R is the rate of change. How much are we paying each month? X is the amount of time. So let's say we're paying it off in 12 months. And then notice the value inside the parentheses will always be less than 1 because it's 1 minus some value. And we know that R is never going to be negative. So it's 1 minus some value, so that means it's going to be something less than 1. Now, how can we recognize growth versus decay in graphs? Well, growth is always going to go up. Decay will always go down. So exponential growth goes up, exponential decay goes down. How do we recognize it from equations? Well, exponential growth equations always have a base value greater than 1. So it could look like this. Y equals 3 times 1 plus 0.4 to the x. So obviously that's greater than 1 when we add those together. Or it could be something like this where they already added it together for you, where it's y equals 3 times 1.04 to the x, which obviously this number is greater than 1. So that's growth. Decay always is less than 1 inside the parentheses. So we have something like this, y equals 1 minus 0.4 to the x. Or they might have already done it for us and had y equals 3 times 0.06 to the x, which both of these we can tell are going to, when we simplify them, are going to be less than 1. So that's decay. So how can we tell? Let's look at an example. We have f of x equals 1/2 to the x. Well, 1/2 is less than 1, so that is decay. We have 3/2 x. Well, that's bigger than 1, right? Because that's 1.5, so that's growth. 7/8. Well, that's smaller than 1, so that's decay. 4/3, again, that's bigger than 1, so that's growth. And 1/3 is less than 1, so that is decay. Notice it didn't matter that they put a coefficient, it didn't matter that they messed with the exponents. This is the only number that matters. If it's bigger than 1, it's growth. If it's smaller than 1, it's decay. Let's look at a word problem for exponential growth. It says the population of Chicago in 2016 was estimated to be 35,000 people with the annual rate of increase of 24%. What is the population in 2019? So first of all, we're going to go ahead and use our formula of f of x equals a times 1 plus r to the x. And we're going to plug in the starting amount. Well, what did it start out at? Well, it started out at 35,000, so that goes in for a. So this is f of x equals 35,000 times 1 plus r to the x. Then we're going to plug in our rate of change. Well, we can see that it changes by 24%. Well, 24% we need to write as a decimal. So this is really 24.0%, right? So we're going to move the decimal back 2 places, 1, 2. So it should change to be 0.24. And then lastly, we're going to plug in the amount of time. And the amount of time between 2016 and 2019 is 3 years. So this is f of x equals 35,000 times 1 plus 0.24 to the third power. We'll solve that using a calculator. And when we do that, we end up with 66,731.84 people. So that should be the population of Chicago in 2019. Let's look at another example. So it says we opened up a bank account 4 years ago with $300. You have a 7% interest rate on your account. How much money do you have now? So again, we're going to start with our exponential growth formula. So we're going to plug in the starting amount. Our starting amount was $300. So we plug that in for A. Then we're going to plug in our rate of change for R. It says we're going up by 7%. So that's, we move the decimal back 2 places. So that's 0.07 is our rate of change. And then we're going to go by the amount of time. We're going to plug that in. The amount of time was 4 years. So we plug 4 in for X. And then we solve using a calculator. And when we do that, we end up with $393.24. Now let's look at exponential decay. So this time the population in Chicago was decreasing by 24%. So we start here with our equation of a times 1 minus r to the x. We know it's minus because we're decreasing. And we're going to plug in the starting amount. The starting amount was 35,000, and that goes in for A. Then we plug in our rate of change. Our rate of change is 24%, so we're going to move the decimal back 2 places. 1, 2. So that's 0.24. And then we plug in our amount of time. The amount of time is from 2016 to 2019. That's 3 years. And then I solve using a calculator, and I get 15,364.16 people. Let's look at one more exponential decay word problem. So it says you opened up a bank loan 4 years ago with $300. You pay 7% of the remaining balance each year. How much money do you owe now? So again, it's decay because the amount of money we owe is going down. So if we start with f of x equals a times 1 minus r to the x. So the first thing we do is plug in our starting amount. Our starting amount is $300, so that goes in for A. And we're making payments, so we're going to plug in our rate of change. We're paying 7% each time, so it's 7. We're going to move the decimal back 2 places, so 1, 2, so that's 0.07. Lastly, we're going to plug in the amount of time. The amount of time is 4 years, so that's 4. We plug that into our calculator, and we get that now we owe $224.42. There's a video here that shows you how to check exponential functions in Desmos, so you can go ahead and watch that video as well. Let's talk now about how we can use Desmos to check our work when dealing with exponential functions. So we'll go here to desmos.com, and we're going to click on Graphing Calculator. And it should take us to a page that looks like this. Right here is where we can enter the equation for our exponential function. So let's go ahead and do that. So let's say it was y equals 2 to the x. Well, as we can see, it graphs it for us. It shows us what the curve looks like. And we can enter any equation in here. Let's say we had y equals 1/2 to the x minus 5 power. Well, now it has our new equation with our curve going down, and it is half as steep, right? And we can see that it's slid over to the right. So we can graph any equation using Desmos and check our work so that we can see exactly what the graph of the line should look like. So that's how you can use Desmos to check your work when dealing with exponential functions. Let's take a look now at the exponential functions review assignment. So if you notice, our review assignment begins with the learning goals and success criteria here. If we continue to scroll down, we're given some questions. The first one says, what is 3 to the third power? Well, 3 to the third power is 3 times 3 times 3. So 3 times 3 times 3 is 3 times 3 is 9, times 3 is 27. So we'll go ahead and mark that as our answer. And let's go ahead and pick another one. How about this one? A to the 9th divided by a to the 3rd. Remember, anytime we divide, we're going to just subtract the exponents. So this is a to the 9 minus 3. Well, 9 minus 3 is 6, so we get a to the 6th power. It says, which of the following graphs could represent the function below? Y equals 4 to the x. Well, 4 to the x, we know it's going to go up. So this one's out and this one's out, so it's got to be one of these two. And because the 4 is much bigger than 1, we know it's going to start to get steeper. So it should be pretty steep. So this one is the steeper one, so that's our answer. So we'll continue all the way till the end, answering all the questions. Once we get to the end, we'll go ahead and click Next. This will send you to your Before You Go. Complete your Before You Go, and then submit your work on Google Classroom.